Alrighty, so obviously the hard one yesterday was not solved, although I think I have an idea as to how to solve it, just didn't have time. I say as I make a totally predictable excuse. Anyways, let's see if I can do this one. Minimum number of seconds to make mountain height 0. Previously solved this at some point. Medium, you're given a integer mountain height denoting the height of a mountain. You're also given an integer array worker times representing the work time of workers in seconds. Workers work simultaneously to reduce the height of the mountain. For worker I, to decrease the mountain height x, it takes worker times at I plus worker times at I times 2 plus worker I times dot 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 x. For example, to reduce the height of mountain 1, it takes worker times at I seconds. To reduce the height amount of the mountain by 2, it takes workers times at I plus workers of I times 2. Okay, so it's like a polynomial amount of time, kind of. Return the integer representing the minimum number of seconds required for the workers to make the height of the mountain 0. Mountain height is 4, worker times is 211. Output is 3. So you would do what here? One way for the mountain height to be reduced to 0 is worker 0 reduces height by 1, taking 2 seconds. Worker 1 reduces height by 2, taking 1. I see. So they do it simultaneously. So the maximum is the time it takes. 10, 3, 2, 2, 4. So I think this one I should probably reduce it by 2, 3, 3, 6, 7, 8, 9, 10. So this thing reduces by 2, by 3, by 3. Maybe this should be reducing it by 4. This reduces by 1. 1 by 4 seconds. 2 here, or 3 here. Take 3, 6, 9. So it can reduce, no, it should reduce 2 here. Worker 0 reduces by 2, taking 9 seconds. 3, 3, 2, 6, 4, 10, 4. Okay, I understand it. So it's not quite polynomial. Is it quite polynomial? I mean, it's t times 1 plus 2 plus 3. So the time is 2. It would take 2 times 1 plus 2 plus 3, 6. And that will be 3 reductions. Okay, yeah. So what's the best way of doing this? I think I can do a binary search, maybe. I guess the time, I guess the minimum number of seconds. And I see if it's possible to be done within that time frame. Yeah, I think binary search is probably the way here. So for binary search, I need a O of n algorithm or O of n method that verifies whether or not it's possible to be done at a certain time. So I generally call it is possible. Let's say to be done in a certain time. So this is going to return a Boolean. This is O of n method that verifies if it is possible for a certain time to reduce the height of the mountain completely. So given a certain time, basically I'm going to use up all the time, or every worker is going to spend up to that amount of time to reduce as much height as possible. So reduction is going to be 0 for every so for every, let's say, t in worker times. I need to convert the time. I need to determine how much reduction can be done in a certain time, a certain overall time given a worker time. So it'll be something like let's say this is total. Too many t's. I'll say if the total time is equal to t times 1 plus 2 plus dot 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 plus x. I'm solving for x, which is the reduction. So t equals t times x times x plus 1. No, is that right? X over 2 divided, or yeah, x times x plus 1 over 2. It's quadratic. Don't really want to use the quadratic formula to solve this. That'd be t divided, it'd be 2 times t divided by t, 2 times the total time divided by the worker time is equal to x squared plus x. My brain is slow as molasses. One plus 2 plus 3 times t times the worker time equals the total time. Total time divided by t. One plus 2 plus 3. Oh boy. I can do something really janky. Oh boy. How many workers are there? There are 10 to the 4, 10 to the 6 workers. Yeah. Do. 10 to 6 workers. Mountain height is up to 10 to the 5th. I think I should initially sort the worker times. There could be some optimizations there. Could go slowest worker. So the fastest worker, which is to say the worker time with the smallest number, should be able to do the most reduction. So I should have a high number for this guy, and then all the other dudes that follow it would have a lower number reduction. I wonder if I can do a heap here. Could do a heap maybe. For each worker, add in the reduction to the heap, and then just keep on pulling out the lowest value in the heap each time. Until I get to the number of reductions that I would need. The heap would be pretty large, 10 to the 6th. I would have a fair amount of ten to the 6. Alright, let's just do a simple heap. I guess I think the other things I'm thinking about are much more complicated. So, heap method. Just always use the next lowest cost for reduction. So I'll say I'll have a heap for every time and worker times. Maybe I still sort. Did I sort? I probably shouldn't be sorting here. Actually, worker times, I think I might just heapify it, right? Worker times is just the initial values for all the worker times, so it's this is the initial cost. But I don't know how many times I've used it, so I might need to actually have a tuple. Yeah, I might need to have a tuple. So the heap is initially tuples, that is the time 1, which is the first time I've used it, for every time in worker times. And then heapify dot, I think it's heapify is the call. heapq.heapify, yeah. heapq is already imported. So for every time in worker times, no, actually, I think that's it really. So I think here how would I track this actually? So keep track of a total time. And keep track of number of reductions. Keep track of the total time and the number of reductions, maybe. That doesn't seem great. Always use the next lowest cost for reduction. Yeah, it's actually not that easy. Or not that straightforward. Maybe I just go back to binary search. Define if it's possible total time reduce given the current time and the total time, how to tell how many times I x squared plus x equals 2t divided by t, 2 total time divided by worker time. Just approximate it as x squared. That's so bad. I don't have a precise value. x squared plus x times x plus 1 n times n plus 1 over 2 1 plus 2 plus 3 plus dot dot dot. So what this is 2 times t over t, no, total time divided by t is equal to something of the arithmetic sum. If I can make that into an array, whose values is the summation of the partial series, and I search for the value that is the quotient t divided by t in that array. That would approximate x. X would be the index within that. So I use like bisect left or something. Wow. I think this would work. It's just not very clean, elegant. K in range, say, is 10 to the 5th. So K in range, what? Actually, I can do while loop here. Say k equals 1 while s is the sum, while sum is less than 10 to the 5th. Let's do the partial sums. It's going to be an array. S plus equals k, k plus equals 1. Partial, append the sum. How big is this? Jesus. 1 plus 2 plus 3 plus 4 plus 5. Okay, that seems right. It's pretty darn big, huh? Yeah, whatever. Keep that. And then I'm going to do the is possible here. So for every time t, so every worker time, I'll do the quotient equals, no, the quotient is here. Quotient equals work total divided by time, total time divided by worker time. and then reduction plus equals bisect left. This is horrible. This is n log n workers log n to find the thing, and then I have to do this like n log n to do binary search. All right, well, let's see how this goes. Bisect left of the array first, I think. So the array is partial, and then the value, which is the quotient. Okay, just need to consider when that's should be +1. So if my guess was 3 divided by 2 is 1.5. So 1.5 searching into here is going to give me 0. No, it's going to give me, I think I need to round this down. I need to make this actually quotient is just 1. And then if I search for 1, it'll give me 0. So should this be +1? I think that might be right. If the total time is 3, worker time is 1, 3 divided by 1 is 1, or 3 divided by 1 is 3, and then quotient is 3. That gives me index 2, or index 1, and then index 1 plus 2. Maybe this should be bisect right. 3 bisect left would give me index 1, but then if I had 2, 2 would also be 3. I think that should be my bisect right. Bisect right is the post insertion. So 1 would be giving index 1, 3 would be giving index 2. Yeah. If reduction is greater than or equal to the mountain height, return true. So I guess return if the total reduction is greater than or equal to mountain height. Okay, double checking here. So if my guess is time 12, let's say time 12, worker time is 2, 12 divided by 2 is 6. 6 bisect right would give me index 0, 1, 2, 3, index 3, which is the number reduction, yeah. And then if it was 12, 12 divided by 4 is 3, that should give me index 0, 1, 2. 2 reduction for worker 3. And then if my guess was 11, 11 divided by 2 is 5.5, rounded down is 5. 5 would give me a reduction. Bisect right would be index 2, 0, 1, 2. I think that's right. Okay. Okay, so let's say the binary search would be low is equal to, what is the low time? Low is total time. 1 second maybe. The highest total time is infinity. I should come up with better ones here. While low is less than high. Low should always be impossible, and high should always be possible. So I think low might even be 0. Just to guarantee that's not possible. Mid is equal to low plus high divided by 2. I'll do return value equals is possible, trying the mid value. If it's possible, then I want to try lower the high. So the high is equal to mid plus 1, or is it mid? I think it probably should be, so if they're adjacent, let's say they're like total time is, mid is 5, or low is 5, high is 6. Mid would be at 5. Mid would be at 5. I want to say this should be mid plus 1. No. It should be mid because it was 5, 6 and it worked. Then I can't just make it 5, 6 again. So it has to be mid. Yeah, high has to be mid. Else low has to be equal to mid plus 1, I want to say. If it's 5, 6 and that didn't work, then low needs to increase past mid. And then when it stops working, then low and high should be the same value. And it should just be the low value that works. Or the high value that works, it should be the same at that point. Excellent. Just nothing works. Did I have return 0 at some point? No, it's just low. Oh boy. Huh. Low less than high, mid. If it's possible to do the mid, then you want to try lower the value. So high becomes mid. So it's possible to do 5, and it's at 5, 6. If 5, 6 is possible, then 5, let's say low is 0, high is 10, mid is 5. Let's say that's possible. High becomes 5. Mid becomes 2-ish. not possible, then low needs to increase. Right. Okay, I guess I just need it. I need to go ahead and just print out the not a number. Interesting. 0 plus infinity divided by 2 is not a number, maybe? Okay, maybe infinity is just not good value to use. What would be a more reasonable thing? I guess maybe if the first worker did everything, or the lowest worker did everything, is this worker does everything, everyone does 1. Mount height is 10 to the 5th. Not a number. Okay, let's just make it something really large that I don't think is possible. Let's do 10 to the 9th. Okay, well, that did definitely clear it. What is a more reasonable guess than 10 to the 9th? 10 to the 5th. In the worst case, Alright, I'm just going to try submitting in this and see how this goes. Goes wrong. Is this bigger? Yeah, 10 to the 9th is not big enough. It has to be like 10 to the 10th, maybe. Still not big enough, or still not correct. Interesting. So start it off with what is this number? 5. This is a huge number. So start off working, and then it got bigger. This one probably should have been returning false, I think. I think I see it. I don't think my array has gone big enough. Yeah, I see. I stopped at a certain index for this array, but if the mountain height is this, then it needs to actually go all the way to 5 million or however much this value is. Yeah, I see. Because the mountain height is... Yeah, this is too big, huh? It would need to be 10 to the 5th. Yeah, I need to have 10 to the 5th values in the pre-compute, which is quite large. Yeah. The edge case is just too big, huh? Ten to the 5th values. 10 to the 5th is 100,000. And I really don't want to use the quadratic formula. X times x plus 1 over 2, or x squared plus x minus 2 times total time over time. So if I have a worker time and if I have a worker time fill out more partials if I find that the bisect right is not far enough, maybe. Oh. Okay. So just this thing is just not big enough. Yeah, this needs to be k is less than or equal to k is less than 10 to the 5th rather than s. I wonder if there's a better way of doing this rather than doing binary search. The workers work simultaneously. So I do some sort of heap, if I have a certain time, have the lowest cost, lowest cost reduction, one plus two plus three plus four, have this thing scaled to a certain time. Scaled to a certain time. But total time I'm tracking. Total time is currently 0. Look at my heap. Lowest cost is 1. I make the total time 1. And put back on the heap 2 to indicate that it would take an additional 2 time past the 1. No, maybe I put it back on the heap 3. Heap 3. To indicate that the next time it needs to be reduced, it needs to be 3. And then I increase time, increase the time each time. Wow. So the heap has the time that it would take for the worker to reduce the next one, their base costs, and the number of reductions they've done. Does that make sense? N is the mountain height. N is the mountain height. La 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 la. So heap is time maybe the number of reductions and So it'll be 1. Okay. For every time in worker times. Yeah. Pretty bad. Not pretty bad, it's just bad. Whatever. Okay. Current time is, let's say, 0. Heapify the heap. While, say, the reduction is also 0. While the reduction is less than mountain height. I'm going to make current, next time is going to be heap dot heap, or take the top off the heap, so heap pop. Next time count and the base time. Current time becomes next time. Current time becomes next time. Reduce plus equals 1. And then something like for heap push onto the heap, the next tuple, which is going to be this should be 1 plus 2, so it should be next time plus count plus 1 times the base time. Count increases, so count plus 1, base time is the same. Yeah, and then something like while heap at 0, the top of the heap has the same starting time. Then I need to do this to the other ones as well. Guess. Up in the heap. Maybe I can do a push pop. Let's say I need to know the count and the base time at the top of the heap. And then it just is heap pop push. Pop. It should be next time plus count plus 1 times base time there. Count plus 1 base time. Reduce increases. think reduce is actually a function. I think this is colored differently. Yeah, it's a function name. Probably shouldn't use that. What is this thing called? It's called reduce. I'll just call it lower. Lowered. I'll call it shrink. Shrink. Okay, so initially shrink is 0, and make a heap. While I still need to shrink it. I'm looking at the lowest costs of all the possible shrinkage times, where it's the... No, that's not going to be working right. Yeah, it's just not going to work. Is it not going to work? First element of the tuple is the actual total time for the next reduction. The total time for the next reduction. So maybe that does work. Next total time, the count of the number of times it's been used. This worker has been reduced to shrinking the base time of the worker. First one of each of those is just their initial worker time. Current time becomes next time. Shrink increases by 1 by using that. I should probably use heap push pop here as well. Heap at 0 is that. And then heap push pop. Heap pop push. Which is to just replace. Next time plus, so it's going to be 1 plus 2. The ties are going to go in the wrong direction. Is it? Guess maybe not. Maybe ties are fine. Yeah. Total time is still the main tiebreaker. Count plus 1 base time. So 1 second becomes 3 seconds. 1 plus 2. And then 3 seconds becomes 6 seconds. 3, 2 plus 1, 3. 3 times 1. Okay. And then while that is still... While there's other things that have that same time frame to reduce, then remove those and update them. Okay. Whoops. I forgot to heap. Unmatched. This should be a tuple. Oops. Oh, there's missing parentheses there. A push, a pop push. Isn't that? Is it he push pop? It doesn't make that much of a difference. He push pop versus he pop push. It just guarantees that there's going to be at least one element at all times. It's probably pretty slow. Yeah, pretty slow, huh? Oh my god, that is such a bad roll. Well, alright, I mean, it's pretty darn late, and I'm traveling for a very long time today. So, I'm just gonna call it here. Feel really bad about this. Okay, but in any case, summary here is gonna be kind of a journal. Tried doing a binary search algorithm to solve, but couldn't get the finite points to work. So in the end, used a heap method to solving. Not great, but a bit tired to do better at the moment. For heap method, basically we'll track the lowest total time, track the next time when a reduction could occur by any worker, and at every step, every reduction in height will update / move time to the next time where a worker would reduce height. Use a heap to keep track of the lowest, the min, next time when this occurs. If there are multiple reductions at that time, for example, t equals 12 for example 2. For example, in number 2, t equals 12 has three reductions by workers 1, 2, and 3. Index 1, 2, and 3, whose times are 2, 2, 4. So yeah, heap tuples in heap need to track the next total time of reduction, comma, count of reduction by worker, and the base worker time in order to know how to generate the next tuple when that worker reduces the height. So just thinking through it, so if you have a base time of 1, the first time that worker would reduce would be at total time 1. If the base time is 2, then the first time that worker reduces would be at total time 2. So if, let's say their base time is 2, then let's say that you figure out that 2 is the new time. So you say that you shrink increase by 1 by using this worker, and then the next total time when this worker would shrink the height would be at 2 plus 2 times 2, so at times 6, which hopefully makes sense. So if we have a base time of 2, then the first time that it reduces at time 2, next time it reduces at time 6. So the math there is the current time, which is 2 plus 1 plus 1, the number of times that they've done reduction, plus times the base time of 2. Maybe this works better with 3. So the first time sum with base of 3 is 3. The next time would be 3 plus 6, which is 9. So 3 plus 2 times 3. Their number of reductions is now going to be 3, or I guess it'd be 2, yes. Count plus 1 is 2. Base time still base time, so yeah. And then everything else on the heap that has that same reduction should try to reduce. Updating. Time complexity, this can be O of n log n in order to create the heap. Actually, it's n log n. It might be n log n squared. The first heapify call is going to be n log n because the first heapify call has everything in the heap, I think. Okay, I think since heaps generally will need to work in a pseudo-sorted fashion. Could be something slightly worse, like O of n log n. I'm really not sure. Space complexity could be O of n in order to maintain the heap.